So the final speaker of the morning session is Jarvis Haupt from University of Minnesota.
Okay, so I'd like to thank Robert and thank the event organizers here. And before I get started, also wish Ingrid a very happy and special birthday celebration. I was thinking about this during the opening remarks, and I came to the conclusion, at least with my quick calculation, that 59 is also prime over the Gaussian integers. So it's a especially kind of exciting event. So. Okay, so what I want to talk about is just some work that I've been doing recently that I call compressive saliency sensing. So I'll sort of set this up in the context of sparse inference, but sort of talk about a generalized notion of sparse recovery that has some, I think, kind of interesting applications, and then say a few words about the kind of my longer term visions for some of these ideas. Okay, so I have a slide like this not to be overly provocative, but to maybe highlight this word interesting. So what's interesting about sparsity? Obviously, we're all here and we're all excited about this as a research area and as a notion, as a modeling characteristic. We're all obviously very familiar that this notion of sparsity is ubiquitous. So in your digital camera, or maybe we don't really use digital cameras anymore, your pocket, your mobile device, this sparsity is kind of an enabling characteristic or enabling phenomenon for digital imaging. I maybe won't dwell on this too much, except to say that now you're acquiring, tens of megapixels of images, and you don't really store all the raw data. You use sparsity as a means of compression. So what you actually store is some sort of reduced dimensional representation of the image. Obviously, sparsity shows its face in a lot of aspects of science and engineering and medicine. Imaging things from astronomical imaging to inside the human body, and also in communications. So this is a fairly classical notion of sparsity, that if we take, say, a continuous time signal that happens to have just a few frequency components, if we sample, look at a DFT, that this would be sparse in the Fourier representation. Okay, so for our interest here, we usually talk about sparsity in terms of this kind of vector model. This is one of the most common kind of modeling approaches in compressive sensing, so we'll adopt that here, and for now we'll think of this as a vector. Later on I'll generalize this just a bit. So when we talk about sparse signals, we'll think about a vector. We'll say its dimension is n and there's some number of non-zeros. I'll introduce just a bit of notation. This signal support, this is a common notion, just a set of locations where the signal is non-zero. And when we say sparse, we're meaning that the number of non-zeros, the number of degrees of freedom in this length n or n-dimensional object is much smaller than the ambient dimension. So this k is the number of non-zero signal components. And again, these are just the kind of stylized examples. So, okay, so why is this interesting from an inference perspective? Obviously, sparsity has a lot of interesting kind of applications in modeling. In the last 10 years or so, we've noticed that these notions can be used to regularize certain inverse problems. So this is just a stylized representation of an example from a paper by Candace and Romberg in 2006. So if your object is to recover some high-dimensional object, say an image, what I'm showing on the top is a depiction of traditional sensing. So if you think about your image as just a collection of pixels and you vectorize that into some length n object, traditional sensing just corresponds to collecting one sample per pixel. So the number of observations matches the ambient dimension, and of course in that case reconstruction is sort of direct and obvious. Compressive sensing describes this notion where you're trying to acquire, again, the same kind of image, but you have a generalized kind of linear observation model. So no longer we're just collecting point samples, we're taking these linear combinations of pixels. And the punchline here is that, and these are numbers again from this paper, here they argue that you can reconstruct this image from something like 70,000 complex noiselet measurements, or which would be about 140,000 real measurements. So the idea is you're getting a downsampling by about a factor of 10, and more importantly, the kind of recurring theme in compressive sensing is that we can recover or do some inference on objects that are k-sparse using something like k log n linear measurements. So no longer do we need to have to be measuring at sort of the ambient dimension, but closer to the number of degrees of freedom, closer to the information rate of the signals. And I say this is a recurring theme without going into too many details, but this is this same kind of sample complexity shows up in a variety of inference tasks, from reconstruction to model selection to in the presence of noise and so on. Okay, and I say this just sort of, I guess I could have taken a list of the names of the attendees here and sort of put this in as a list of people that are working in sparse recovery and sparsity-related fields. So with apologies to people that I may have inadvertently not listed here, I just want to indicate this is obviously an active area, and there's a lot of different techniques that have been examined for sparse inference in a variety of settings. Okay, so what I'm sort of interested in is a problem that kind of piqued my interest some years ago. So I'm going to use a motivating example and talk a little bit about beyond this notion of sparsity. I'll call this a simple extension. So probably many of you are familiar with this work of Donahoe and Tanner from several years ago, where they were looking at counting the faces of these randomly projected polytopes. And this was a way of establishing this exact equivalence between the L0 and L1 kind of recovery problems. And so they had, essentially they looked at cross polytopes and simplexes as models for sparse signals having positive and negative elements or non-negative elements. And from my perspective, I think they kind of considered this third class just to kind of round out the investigation. There's one more regular polytope that exists in high dimensions, and that's this hypercube. And so what they said was, well, we can envision this as describing a class of sparse-like objects called simple signals. And so just in words, kind of translating their model for my interest here, you can think of these simple signals as nominally binary vectors. So they're, say, n-dimensional vectors, and they have something like n minus k elements that are either 0 or 1, and there's some number of outliers. So there's k of these elements that are strictly between 0 and 1. And when they were talking about these to motivate their kind of phase transition work, they described this as a model for, say, radiation absorption spectra. So here I'm just showing a figure of how radiation is absorbed or transmitted through the atmosphere across a wide array of wavelengths. In the infrared region, chemists use this as sort of a chemical fingerprinting technique, but more generally you can think about this as a way of determining kind of constituent materials between source and destination. And the idea is that these signals have kind of a bang-bang characteristic, right? So there's levels of 0, levels of 1, and then there's something kind of going on in between. Okay, so signal model notwithstanding, we have this k-simple kind of signal model, and the question that Donahoe and Tanner looked at was, can we recover these types of signals from compressive samples? And the answer is yes, but with a little bit of a caveat. So again, maybe you're familiar with these phase transition ideas, but here's just an overview of this kind of recovery approach. So imagine you have one of these k-simple signals, and say it's n-dimensional, and you collect these linear measurements, say Gaussian random projections. And what we'd like to do is try to recover this, so we have some sort of convex program here. We can have this equality constraint, and in this case a box constraint, because we know all the elements of the signal are between 0 and 1. And we want to minimize some sort of energy that penalizes non-simplicity in this context. So you could look at the cardinality of the number of elements that are not 0 or 1, or some sort of energy or something like this. Turns out that essentially almost any cost function will work here. And the point is that you're probably familiar with, I don't know if the pointer will work here, these phase transition curves. So there's two axes here. Along the x-axis, this is essentially how much I'm undersampled relative to the dimension. And the y-axis is how much I'm oversampling relative to the sparsity. So what this basically means is that if I'm oversampling the sparsity by a lot, I'm going to be low on the y-axis. And if I'm taking a lot of samples relative to the ambient dimension, I'm going to be far to the right. So down in this lower right quadrant is essentially the area where things should be most favorable. And these phase transitions essentially indicate as long as you're below and kind of to the right, you can recover these signals with probability tending to 1 as the dimensions sort of tend to infinity. And these curves just represent what they call phase transitions. So this tells essentially for which types of signal classes when you can recover, when this L1 will actually give you exact recovery. I don't want to dwell on this too much except to say that for signals that are sparse in the method that we understand, having either non-negative entries or entries that are positive or negative, you see that actually we can get exact recovery. If you look over here, where the number of measurements relative to the ambient dimension can be sort of very small, on the order of something approaching 0 for those signal classes, while the kind of anomaly or outlier here is these simple signals. So what this basically says is that if I want to try to recover these simple signals with compressive measurements using this kind of an approach, some kind of a convex approach, I can't recover these signals unless I collect at least n/2 measurements. And so this was always something that was a little bit kind of interesting to me. I understand, this kind of rounds out the study of all the regular polytopes and counting their faces under random projection. But this kind of got me thinking about, what's really interesting in these contexts. So can we think about this signal model in a little bit different way? So here I'll come back to this word interesting, and this was meant to be kind of a motivation or food for thought. So what is interesting about these simple signals? In general, you might be interested in recovering these kinds of signals, but if you think about a little bit of a relaxed criteria and say, well, maybe I'm not so interested in recovering these constant values, but just kind of what's happening in between. So we might think of this like an outlier detection or anomaly detection kind of problem and say that the elements that are neither 0 nor 1 are sort of what's interesting about this signal. These are the outliers or the anomalies. And now you can ask kind of a related question is, if I'm only sort of interested in localizing or identifying or finding these outliers, can I do this with something on the order of k log n measurements? Can I get back to kind of what I expect or hope with compressive measurements? And that'll sort of be the topic of what I'm going to talk about. And what I want to talk about is sort of a generalized framework under which we can analyze problems of this flavor. So this is just meant to be a motivating example, and I'll discuss some other problems that fit into this kind of general framework. Okay, so the essential idea is that we're going to think about these new kind of recovery problems as generalized sparse recovery tasks. And in order to do this, I'm just going to introduce a little bit of preliminaries and notation to formalize the model. So we're going to have a data model where we consider a collection of n, say, elements. Here I'm going to use capital X to represent this data before I use the lowercase x, but here this is just to typify that I can have a collection of, for instance, scalar values x1 to xn, and then this collection of elements would be a vector, kind of like what we've seen so far, but these could also be multivariate and so on. So we have, our data is just some collection of a possibly large number of data elements. Okay, so now this notion of sparsity, how can we generalize this idea of sparsity? And one way to do this is to do this in terms of something that I call a common set. So I'm going to denote this by script z. And I'm going to use this set to describe which elements are uninteresting in some sense. So just to formalize a bit of notation, I'll give some examples in just a minute. But just to extend the notation just a bit, if I have a collection of data elements, say n data elements, where n minus k of the elements belong to this set script z that I'm calling the common set or the uninteresting set, and k do not, then I'm going to call this type of data k salient. So it's sort of a generalization of sparse. We're talking about salient, and this is terminology borrowed from computer vision, and we'll see why I do that in just a few minutes. Analogously, we can think about the locations of these outliers as some kind of a generalized notion of support. So let me call this the salient support. This is just a set of locations where the element x does not belong to this common set. Okay. So as with compressive samples, we're going to collect these kind of linear measurements. So we'll take essentially sums of these data elements with some coefficients aij. And I'm going to say explicitly that these coefficients should be chosen from some coefficient set I'll call script c. So this could be a subset of the reals or complex. Here we'll deal with the reals. And now our goal in this kind of generalized framework is to identify the salient support. So the model selection problem in traditional compressed sensing is to find the locations of the non-zeros. Here I want to find the location of the interesting elements. So the locations where the data is not, the corresponding data element does not belong to this set script C. Okay, so this is the overall problem. In order to kind of axiomize this and give some conditions under which this is possible, I'm going to introduce just two assumptions, and I'll argue that these are fairly mild and intuitive and maybe in some sense benign. They're assumptions on these pairs. The Z is this common set and C is this coefficient set. So assumption A1 I call restricted closure under addition, and the essential idea here is that if I take a collection of elements that are in this uninteresting set, and look at certain linear combinations. It doesn't necessarily have to be all linear combinations, but just linear combinations where the coefficients are this little c sub l are elements of this coefficient set script c, that if I look at these linear combinations, they will also be elements of this set script z. So in other words, if I add together uninteresting elements, they'll remain sort of uninteresting. I say restricted closure because we don't really require this to hold over all the reals, just over this coefficient set. The second assumption is that if I have a sum of elements that are uninteresting, and along with one element that's interesting, that doesn't belong to the set Z, that I can identify that I can say that this sum does not belong to the set Z. So I call this single outlier identifiability. So in words, this is just a way of kind of formalizing the notion that if I add together a bunch of things that are uninteresting, the sum is going to be sort of uninteresting, while if I have a sum that contains one interesting element, that I can identify it as such. So let's just look at a couple examples. This should subsume our regular notion of sparsity, and in fact it does. So for traditional sparsity, we can think about this common set as just the trivial linear subspace, the zero, just the set containing zero only. And the coefficient set in this case could be the real numbers, or there are others, obviously. This is just one example. The simple signal model fits this criteria as well. So in this case, the common set, the things that are sort of uninteresting to us, are zeros and ones. And in this case, this coefficient set, we have to restrict it to be the class of integers. So if I take integer combinations of zeros and ones, I get something that's, z. So this should be, so this common set here should be the whole, should be the set of integers. I'm sorry, this is a typo here. So another example, we could think about the common set being the set of all rational numbers and a coefficient set of the integers. So if I add together two rational numbers with integer coefficients, that remains rational. And another interesting kind of example of this is multivariate data. So if I think about a common set being essentially the span of some number of linearly independent vectors, just essentially a lower dimensional subspace, clearly these are closed under addition by definition of a subspace, so I can think about the coefficient set being the reals. Okay, so our approach, the typo on the previous slide notwithstanding, the approach is that we're going to think about solving this problem via a proxy. So we have these observations, these linear measurements y, and these coefficients, what I call aij. And instead of dealing with those directly, what we're going to do is create these binary proxies from these elements. So from the set of coefficients, which is essentially you can think of as a matrix, I'm going to create a binary matrix. So M has elements in 0, 1, and the ijth element is just going to be the indicator of whether the corresponding coefficient aij was 0. And from the observations, I'm going to create also a binary vector. That's just the indicator of whether the corresponding observation was in this common set Z. So why would we do this? If you think about a vector x, so think about a binary vector x whose elements just correspond to the locations of these interesting data points, then we can think about this sort of resulting system as a Boolean system, and essentially if we want to try to infer x, knowing m and y, we can think about this as a form of a group testing problem. And in fact, this is a noisy group testing problem. So why is this noisy? Only because by our assumptions, we can only sort of guarantee certain elements of y. So by our assumptions, A1, essentially what this says, remember A1 was essentially this assumption that said if I take linear combinations of uninteresting elements, they'll remain uninteresting. So this implies that if for some observation I, I'm essentially adding together a bunch of zeros where I'm on the signal support. So on the salient support, if I don't include any of those elements in the sum, then I can guarantee that the corresponding observation yi will be 0. And A2, the second assumption, basically says if I have a linear combination that contains exactly one of these interesting elements, then I can guarantee that the corresponding observation will be 1. That was essentially follows directly from these assumptions, but we haven't really made any more assumptions than that. So the implication is that other elements of this vector y, this binary vector, might be erroneous. So this is, in some sense, a non-standard kind of noise model in the group testing literature. This is sort of like a weird form of dilution. What I'm essentially saying is that if I have no positive elements, then I can say that that's a negative test. If there's one positive element in my group, that's a positive test, and otherwise it's kind of a don't know condition. Okay, so just for the sake of completeness, I put the algorithm here. I just want to point out a kind of salient features of the algorithm. Since we're dealing with this as kind of a group testing proxy, and these assumptions are related to us doing tests over subsets of elements, we're going to try to construct these observation matrices, or these sets of coefficients, to themselves be essentially sparse, so they'll be mostly zero. And where that comes in is in this third kind of bullet point where I say collect compressive observations. These coefficients are essentially going to be elements from this coefficient set modulated with IID Bernoulli random variables. Right, so by choice of this parameter Q, we can essentially make this set of coefficients as sparse as we need. And the binary proxies here. Now the support estimation step is basically looking at a set difference between the support of a column of this matrix M, this is called a contact matrix in group testing, set difference with the support of Y. So the implication is that if I'm testing and I have a certain column and that corresponds to a location where there's a true positive, then the support of Y should contain that column. And that's what happens nominally in group testing. In this case, we have a noisy condition, so we have a little bit of a relaxed criteria. And I just want to comment that this is kind of interesting to me, that this kind of inference approach was proposed and examined in a couple of recent works where they called it, in one of these, they called it a combinatorial orthogonal matching pursuit as kind of a, with the comparison with orthogonal matching pursuit, where you sort of look at columns, you correlate the observations with columns of your observation matrix. From my perspective, this is sort of closer to marginal regression, so you're simultaneously sort of correlating your observations with each column of your observation matrix and then comparing it to a threshold. So it's not really OMP-ish, but it's sort of marginal regression-ish. But you can think about it that way. It's sort of the analog of marginal regression for group testing problems. Okay, so the punchline is that under these two assumptions, so we have this pair, Z and C. So Z is this common set and C is this coefficient set. And let's suppose that these satisfy these two assumptions, the restricted closure and single outlier identifiability. And let's say that we have a collection of data that's K-salient with respect to Z. And we suppose that we sort of acquire this data via the procedure I showed on the previous slide. Now, in this slide, one of the things we have to initialize the procedure with is this thing I call the saliency level parameter K prime. So this is basically how salient do I think my data is? How many sort of outliers do I believe that there are? So you may not know that exactly to start with, so K prime, this allows you and affords you some slack in not knowing that. The condition of the theorem is essentially that this be an overestimate for the true saliency level. So K prime has to be greater than or equal to K. And there's also this oversampling factor C, and this has to exceed this quantity I show here. So if these conditions all hold, then you can guarantee that the resulting estimate, S hat, will be equal to the salient support, except in an event of probability 1 minus 2 delta. And this delta, these are parameters that are specified in the algorithm, this error tolerance parameter and this oversampling factor. Now the point I want to make is that the number of measurements here is essentially C times K prime times something that looks like log n or log n over delta. So the implication here is, under the conditions of this theorem, is that if we know the true saliency level up to a constant, in other words, if this K prime is equal to beta K for some constant beta, which has to be greater than 1 by the condition of the theorem, then we can say that this procedure will return this true salient support from something like no more than a constant times K log n measurement. So now we're getting back to this kind of notion of sample complexity that's more familiar in the sparse inference kind of literature. One thing I want to point out, and just in the spirit of full disclosure, and because I think it's kind of an interesting aspect of these group testing problems, is that this sufficient condition here, if you look at it, I'll go back to the statement of the algorithm here. In order for the proof to go through, this alpha parameter has to be between 0 and 1/5, so 0 and 0.2. And if you look at the sufficient condition for this constant, you have 2 over alpha cubed. So just in full disclosure, the conditions of the theorem, which in some sense is often the case in some of these types of proof, the sufficient condition, while it's a constant, might be large. So in some sense, this is an artifact of the proof, but it's also an artifact of just these type of testing problems, it seems. So what I want to talk about now, just for the last kind of portion of my talk, is look at some experimental evidence and a couple applications of these ideas. Okay. So the problem that motivated this in some sense was this notion of simple signals. So what I want to show is just a stylized salient support recovery example for this signal model. So what I did here was generate a signal of dimension 100,000 with, and this is a simple signal, so nominally binary means all but, in this case, all but 100 of the values were 0 or 1, and the saliency level here is 100, so there's 100 elements that are strictly between 0 and 1. Now, if you remember back to these phase transition thresholds, the essential idea here was that if we really wanted to recover this full kind of simple signal, in this case, we need to collect at least 50,000 measurements if we wanted to exactly recover this. My argument is that, in some applications, you can think of this like an outlier detection problem. Maybe you don't want to recover the whole collection of data, but just find sort of where the interesting things are happening. And in this case, what I'm showing in the top panel here is just a zoomed-in version of the original data. If I showed it for all 100,000, it would just be a black bar. So I zoomed in just to show 1,000 elements, and you can see this kind of nominally binary characteristic and the one outlier here at about 800. If you take the data modulo 1, then this is a lot more clear where the outlier actually is. If I look at this third row is the whole data, the whole 100,000 dimensional vector, taken modulo 1, so you can see all the locations of these outliers. And now on the bottom, this is the output of this procedure, and again, with the idea that I've tweaked the parameters just a bit because the statement of the theorem is a little overly conservative. But in this case, the salient support estimate is exactly correct, and this is from 5,800 measurements. So on one hand, you might say, well, this is 58 times the sparsity level, so that's not as good as what we expect, and I completely concur with that point. On the other hand, it's sort of far fewer than what you would need for exact recovery. So this is the trade-off, and some of the looseness associated with this group testing proxy, I think, is maybe inherent to the inference approach that's sort of tied to this, the one I described, the marginal regression-based approach. Okay, so in the last couple minutes, I just want to talk about an application of these ideas in computer vision. So this is something that kind of piqued my interest in some sense. I'll talk about some direct applications of these ideas and then just kind of forward thinking about why I think these kind of ideas could be interesting with an eye towards compressive sensing and sort of inference tasks. Okay, so in computer vision, this is a well-studied area, this notion of visual saliency. The essential idea is that, and I say here, there's been a great deal of work in these kind of problems. The idea is that you have an image and you'd like to, by some automated procedure, identify regions that are sort of interesting in that image. What I'm showing on the bottom here is a subset of images from this Microsoft Salient Object Database, and on the right are user hand-labeled regions of interest. So this is kind of like ground truth. If you want to compare your saliency algorithm to these, with these images, you can compare with this ground truth. So people go in and said, I think this is the interesting region of this image, and this is the interesting region of that image, and so on. So, like I said, there's been a great deal of work in these kind of problems, but the general essence of the problem is you start with an image, you do some inference on that image, you have sort of the full image at your disposal, so you can do all sorts of interesting things, non-local means and whatever. And what you want to output is a saliency map, or sometimes they call this a heat map. So what I'm showing here, this is just an excerpt from one paper. The first column is just a collection of images, and the remaining columns are these saliency maps obtained by different procedures. The essence of the point I want to make here is that if you look, essentially the goal of this is analogous to the task we were talking about before. You have some collection of objects. Here you could think of the objects as being maybe small patches of the image, and there's some subset of those that are sort of interesting, whatever that means here, salient. And at the end of the day, I don't really care to reconstruct the image. I just want to sort of get an output of what's interesting. And presumably this might be a first step in an automated surveillance kind of application. So this essentially fits this model I was talking about. As long as the data model fits, then we can use this kind of procedure. And it's for the reason I said before. We can think about this notion of saliency as a generalized form of sparsity. So in one of these images, I can say, well, these are the regions that are sort of interesting, and the rest is uninteresting. Okay, so just a few minutes here, I guess. basically what this relies on is a subspace outlier model for saliency. So if we think about our original image and chop it up into 10 by 10 patches and think of that as a matrix or a collection of vectors, the model we're going to use is that most of these vectors live in a common low-dimensional subspace and a few don't. So variations of these models have been used by researchers, including people in the room here, for imaging applications. Is this a good model for saliency? Well, it seems to do a pretty good job. So for some of these test images, if you just look at the patches that have residual energy outside of, say, a 5-dimensional subspace that's learned from the data itself, this is essentially what you get. So this is comparable with a lot of these off-the-shelf kind of saliency methods. The bottom row, what I'm showing here is just when you apply this compressive saliency sensing procedure here, this is 20% of the measurements, and you can estimate these outliers fairly accurately. That was on grayscale images. You can do the same thing in a color plane here, or hue. This is hue. You may not have outliers in terms of intensity, but hue or saturation or anything like this. Okay, so let me just end with a conclusion. So the extension, why I think this is kind of interesting, is you can think about stylized problems where this kind of inference task might pop up. So I'm showing here just a kind of a cartoon. This is Where's Waldo, or Wally, I guess, if you're in Canada. So this is this problem. It's kind of a kid's game, but the idea is that there's somebody you want to find, and there's a sea of people, and you essentially need to do something like exhaustive search, or at least that's what kids do, I guess, when they buy these books. And so what I'm sort of interested in is, could you do something like a compressive Where's Waldo, right? So in this case, what I talked about so far is analogous to a bottom-up notion of saliency where local similarities determine what's interesting. If you think of a top-down model where you come in with some higher-order function, in other words, saying, this is what I'm looking for, can we use this to sort of do compressive saliency sensing and from a few samples say Waldo's here? Obviously, this would have applications in surveillance and these kind of applications. So. Thank you.
So I think we have time for one question, and then Becca is going to come up and explain the mysterious white things. So if there's a question, take it at the back. David does.
So it seems like in most problems that you actually have a block you want to identify, like in the initial motivating example you showed, so you want to identify blocks of time, so you have sort of maybe more of a contiguous version of this. So even in the image case, you'd expect that if you had contiguous blocks that you could identify, put that into a procedure, you might be able to get much better performance if you're getting something that wasn't expected.
Yeah, so I absolutely agree. So the question was, can you exploit some higher structure in your inference task? And the answer is absolutely. So there are some group testing kind of efforts that have looked at exploiting some types of structure, but I think in some sense this might be a kind of a good motivation for trying to look at these kind of cluster structures for these group testing problems. Yeah, absolutely.